So we will move to our final speaker, Denny Wu from University of Toronto. So Denny, if you could start sharing your screen. So Denny is a PhD student of computer science in Toronto and the Vector Institute, working with Jimmy Ba and Murat. So he previously got his undergraduate degree from CMU with Russell, and also visited Rican before. So he worked extensively on theoretical understanding machine learning services system, especially the generalization of overparameterized models. So Denny, please take it over from me. Thank you.
All right, thanks, Atlas. Thanks for the invitation. So am I sharing my slides? So can you see the slides here?
Good.
All right, thanks. All right, so I'm going to talk about two of our recent works, one currently in submission and the other in Europe this year. And I should say I'm actually not sure of how relevant this material is to low dimensionality neural network, but I'll try to make some comments on how our problem setting may relate to certain low dimensional structures. All right. So we're going to look at regression with the squared loss, okay? And I'll motivate things a bit using ridge regression. So here we have n training points and d input features. So the number of parameters to be estimated is also d. We want to understand properties of the ridge regression estimator in the overparameterized regime. So we define a constant gamma, which is the ratio between the number of parameters and the number of training points. And we're going to let this constant to be something that's larger than 1. So there are more parameters than training samples. So here, classical intuition is that as we increase gamma, we're essentially making the model bigger. So you should probably regularize more, because now the model is more capable of overfitting. I actually don't know if anyone believes this, but at least this is one way to think about things. The reality, however, is that even if you do not regularize, the prediction risk or the generalization error can actually decrease as gamma increases. So what this is telling us is that in some sense, overparameterized models can be implicitly regularized by the structure of the estimator or the optimization procedure. So like, for instance, if you're running gradient descent. In the case of ridge regression, it has been argued that overparameterization kind of induces an implicit L2 regularization. And what's funny is that, at least empirically, the optimal explicit regularization, lambda, can be negative in the overparameterized regime. And one way to interpret this is that the implicit L2 regularization is so overwhelming that the explicit L2 regularization has to be negative to partially cancel it out. So this phenomenon has been empirically observed, but we actually don't have a rigorous theoretical explanation for it. This is going to be one of the motivations of our work. All right, so here's our problem setup. So each data point is labeled by some ground truth parameters theta star, or the teacher model, and also corrupted by some label noise. Okay. We're going to look at the generalized ridge regression estimator. So instead of having an identity here, which is going to reduce to ridge regression, we're going to allow for any positive definite weighting matrix. So this obviously includes standard ridge regression, but it can also cover other weighted shrinkage estimators, such as principal component regression. We aim to characterize the prediction risk or the generalization error. We're gonna, the regime that we'll be working in is a proportional asymptotic limit. So we're gonna let the number of samples n and the number of parameters d to diverge at the same rate. And the ratio is gonna converge to a fixed constant gamma, which is larger than 1. This means that we're only gonna consider the overparameterized regime. Okay. And our input features are drawn IID from some distributions with covariance sigma x. And we're also gonna place a prior sigma theta on the true coefficients or the teacher model. So this can be interpreted as computing the base risk. And basically, this is where we actually generalize previous asymptotic analysis on ridge regression, most of which only looked at the case where sigma theta is identity, or whereas we allow it to be something that's much more general. Okay. So I'll briefly go over our formula for the prediction risk. We show that the prediction risk can be described by this equation, which relates to the Sildrich transform of certain matrices and also require taking expectation over certain distributions of eigenvalues. It's important to observe that the prediction risk can be decomposed into the bias term and the variance term. So the variance term is due to label noise, and the bias term relates to properties of the true coefficients or the target model. So I'm actually not going to go into details, but I just want to sort of convince you that this theorem is correct. So here we're plotting the experimental values of the prediction risk or the generalization error alongside our theoretical prediction. So the empirical values are actually computed on like 300 training points, I think. So it's actually not too large. So one thing worth noting is that if you don't regularize, the risk curve can look pretty weird. So it can exhibit multiple peaks. And I think previous works on double descent primarily focuses on the peak when gamma equals 1. But if you regularize, then the trend looks much nicer. And this observation actually dates back to 1992. And also, weighted regularization can easily outperform standard ridge regression. So standard ridge regression is the red curve here. All right. So now for the sign of the optimal ridge penalty. We're going to focus on the bias term, because for the variance term, positive regularization is always beneficial. So the intuition is that if you regularize a lot, so that the estimator shrinks to 0, then the variance is going to be pretty small, right? So previous works considered the case where sigma theta is identity. So in other words, no matter which feature directions you pick, the magnitude of the true coefficients on this direction is going to be the same. In this case, the optimal regularization strength is going to be 0 for the bias term. So when you combine it with the variance term, the optimal lambda for generalization is always non-negative. So now we're going to look at 2 new settings covered by our general setup. When the parameters of the teacher model are aligned with the feature covariance, so one example is that you can imagine that your features are high dimensional, but only a small fraction of them matter. By that I mean the rest of them have like really small magnitude. Okay? So then if the true parameters happen to focus on the large magnitude directions, then I'm in very good shape, right? Like, because my features are useful, so perhaps I don't want to regularize. In fact, we showed that in this case, the optimal regularization strength for the bias term is negative. So you should actually push the parameters away from 0 when the labels are not too noisy. On the other hand, when the teacher model primarily looks at the small magnitude features, then I'm kind of screwed. Right? So there's like a mismatch here. So in this case, learning is quite difficult. And we showed that the optimal regularization is positive for the bias term. So in other words, you should shrink the parameter towards 0, even if there's no label noise. And I should add that this finding is only present in the overparameterized regime. If the model is underparameterized, then the optimal ridge penalty is never going to be negative. Okay. So previously, we looked at the optimal explicit regularization, or ridge regression. So now we're going to take the limit of 0 regularization. So the model interpolates the training data. And we're going to analyze how the weighting matrix contributes to the implicit regularization. So simple observation is that if you have a positive definite weighting matrix P inverse, I'll clarify in a bit why we take the inverse here, then you're going to end up with the minimum P inverse norm interpolate. The reason that this weighted minimum norm solution is interesting is that it relates to the implicit bias of preconditioned gradient descent, or essentially second order methods. In particular, if you start from 0 initialization and optimize the least squares objective using a preconditioned update, where P is a preconditioner, then so first it is well known that gradient descent will find the minimum L2 norm solution. But if you have a preconditioner P that does not change through time, then you end up with a minimum P inverse norm solution, which is defined above. So basically, pictorially, here's a one-dimensional illustration. Gradient descent is going to find the solution that's closest to the initialization in the Euclidean distance, whereas for preconditioned gradient descent, this distance is measured by is weighted by some matrix P inverse. And I should comment that we're allowed to restrict ourselves to fixed preconditioners because the least squares setting is very simple. So the Hessian and the Fisher information matrix are both time invariant. But the drawback here is that we can't really say much about adaptive methods like Adagrad and Adam. So in the literature, a common argument against second order or adaptive methods is that the minimum L2 norm solution, which gradient descent finds, generalizes pretty well. But you often don't get the solution if you use preconditioning. However, it is not clear that the weighted minimum norm solution that preconditioned updates find is going to generalize worse. So our motivation here is to understand how preconditioning affects generalization. So just to give some more context, we're going to focus on the comparison between gradient descent, which finds a solution with small parameter L2 norm, and natural gradient descent, which actually gives you a solution with small function L2 norm. And I should note that this definition of natural gradient descent requires a population Fisher information matrix. So the Fisher needs to be computed on the data distribution P of X instead of the training points alone. But this is a subtle difference. So pictorially, here's a figure on overparameterized neural network in 1 dimensions interpolating 4 training points. So gradient descent, which is a red curve, finds a smooth function because the parameters don't travel much, and the network is basically a neural tangent kernel model. In contrast, natural gradient descent, which is a blue curve, will try to fit every data point locally and then decay the function value back to 0 everywhere else because that's where the function is initialized at. So you can already see that the solution have rather different properties, and we should expect them to generalize differently. And just a comment, I don't really think it's a good practice to do theory on linear models and then be like, aha, we also empirically see this in neural nets, but here we're going to do this anyways. So recall that the generalization error or the prediction risk can be decomposed into the bias component and the variance component. So the bias term tells you how well you're learning the teacher model, and the variance term describes the stability of the learned function under label noise. So now we're going to analyze these 2 terms separately and determine the optimal preconditioner for each term. So let's first look at the variance term. We're able to show that natural gradient descent actually achieves the optimal stationary variance. So in other words, when the labels are noisy, we can expect natural gradient to generalize better under interpolation. So again, the caveat is that you need to use a population Fisher. So this finding is also supported by neural network experiments in a student-teacher setup, or essentially distillation. So we observed that natural gradient descent, which is a blue curve, becomes beneficial as the amount of label noise increases. So from left to right, you can think of this as starting from low variance regime to a high variance regime. And in practice, the population Fisher needs to be estimated from additional unlabeled data because the model is overparameterized. So if you decrease the number of unlabeled data, we're actually going to lose this advantage of low variance, as shown by the orange curves here. And I should say that we're not really advertising natural gradient descent when data is noisy, because in such scenario, one should obviously regularize or early stop. But we're looking at interpolation mostly because we're just trying to understand how the implicit bias of these optimizers affect generalization. So now for the bias term. We show that under certain assumptions, the optimal preconditioner is going to depend on the target covariance sigma theta, and also the eigenvectors of the feature covariance U. So U is the eigenvector matrix of sigma x. So in practice, the orientation of the true parameters sigma theta is usually not known. So you can interpret this as a no free lunch result. So the comparison between gradient descent and natural gradient descent is going to depend on the alignment between the 2 covariances discussed earlier in the negative ridge result. When the parameters of the teacher models are isotropic, then gradient descent is going to win. You can see this from the red curve. Okay. But when the 2 covariances are misaligned, remember that this corresponds to the difficult learning problem, the natural gradient descent, which is the blue curve, is going to achieve lower bias. We're also able to observe this trend, this kind of trend in neural network, but the construction is rather artificial, and I don't think it's very robust. And we're also able to prove that this trend is roughly preserved under early stopping. And in the paper, we discussed potential ways to achieve the bias variance trade-off, and we have a convergence rate analysis for non-parametric least squares, so regression in the RKHS under similar setting. So if you're interested, please come check out paper. Thanks.
Okay, thank you so much. I think we got I think got a question from Chong. Chong, do you mind unmute yourself and directly ask?
Yes, sure. So thank you, Denny, for the great talk. So just a question, because from your talk, the aligned and misaligned case have drastically different results. So just want to get a sense of which case is more practical or more relevant for practice.
I see. Okay, that's an interesting question. So I guess okay, it depends on what we mean by like practice, right? So if you're thinking about deep neural network, then I guess the most conservative answer is that this analogy may or may not apply. But here's just a rough intuition about this kind of alignment, right? when you have a aligned signal with the feature covariance, that means your features are very useful. Okay, so that means so in the case of neural network, you can probably think of this as saying that your network architecture is kind of well aligned with this underlying task. So for instance, CNN on images, things like that. But the misaligned case is sort of saying that the features that you extracted from your model doesn't really tell you much anything about the true function, the function that you try to learn. So this kind of happens when you have like a model mismatch, right? So if you're trying to, my previous example would be like to use like a transformer to learn images, but this is actually not a good analogy because transformer actually works pretty well. But essentially, I think this misaligned case is going to be more relevant when you have this kind of model class mismatch. So I guess that's like the intuition for, I guess, neural network optimization. Of course, in practice, like which regime you're at is going to be a different question, which I actually don't know. But my feeling is that since we've spent a lot of time to sort of search for good architectures, right, and manually design like different hacks and stuff, we're more likely in this kind of aligned regime.
Yes,
but I'm waving hands here.
Yeah, I think that makes sense because it's also kind of, we're relying on this kind of prior bias from the network.
Right, exactly. Yeah, this is essentially saying that you have the right inductive bias.
Yeah, yeah. Great, thanks.
Okay, so do we have any further question? We have been significant all the time, but I hope everybody has thoroughly enjoyed this because those are so many great, interesting talks. So if we don't seem to get more questions from the audience, Denny, thank you again. And I'd like to take a chance to thank all those invited speakers in the last session. I hope you have been enjoying the workshop, at least I did very much. And just the final logistics thing, we have recorded all the talks, and I think we got a consensus for everybody to share their slides. So allow us a few days, and we will share this video and share the slides by sending a link to all registered participants. If for any reason you have not registered, just send an email to one of the organizers, and we will get back with the link if that's appropriate. I guess I will just represent all the organizers and just say thank you to all the participants, and thank you for your support. Thank you for attending. Hopefully we'll get another chance perhaps next year to get together again. Thank you very much, and I hope you enjoy your remaining of the weekend. For people in US, please enjoy a good Thanksgiving vacation. Thank you very much.